Good afternoon, everybody. My name is Chet Hall. I'm a senior data scientist here at the AES Corporation in Indianapolis, Indiana. And I'm very happy to be talking to you today about some things that you may have never heard about. And so in spite of my usual, I never show the wall of text, but here I'm showing you the wall of text. I'm bolding these terms, which were in my abstract, not so that you can read the whole abstract again, but you can if you want, mainly just to show you the terms that I'm going to talk about a little bit later, most of which I did not understand even after a year and a half of being a data scientist, but prior to starting this project. So just some context. We're talking about scaling analytics, scaling data science, managing data, which involves also data governance, which is a term that I'll use a little bit later also as well, which we hadn't really done much of at AES until this year. The harmonization of data, which is the crux of this talk, and the medallion architecture, which is this idea of having bronze, silver, and gold data. Of course, it's not always exactly like that, and I'll show this on a couple of slides, but all of this is key for enabling analytics and business intelligence. And a lot of this is kind of the stuff that you need to do before you actually start doing what you think data scientists do. So that's basically what all of my 2024 and much of my 2025 was and will be about. But before I get into that, my journey, just my one slide, maybe two slides. I'm from upstate New York, where the land of great white wines and the Buffalo Bills, who just survived a fake punt pass yesterday, so very excited about that. I went to college at the University of Virginia, and I did an RU fellowship at the University of Rochester after my junior year, and that's where I got into star formation. I took a brief stint teaching in Guatemala, where I learned a lot of the Spanish that has been very useful in several of my jobs, including my current one, because AES has a large presence in Latin America. And then I went out for 6 amazing years, where I met Jeff and many others who are in the ATDS sphere out at UC Berkeley doing my grad work. Graduated in 2014, did a postdoc. I was a Jansky Fellow of the NRAO, but working at Harvard for 3 years. And then after that, I did another postdoc, which is basically a term-limited assistant professor position at the NAOJ. I went briefly to headquarters in Japan, but then I spent most of the 5 years down in Chile working at ALMA. That was basically the best job ever. But during that time, the pandemic hit and life kind of happened. I had 2 kids, and astronomy just was not working out. And I'm happy to talk about that after the talk or offline. And without further ado, astronomy was great. Worked on hardware. That's me inside a receiver cabin of a Karma antenna in California during grad school. I went up to the high site at ALMA at sunset, which never happens. That's the picture that I took down there on the bottom. Totally amazing. I wrote a lot of papers. This thing here on the right is a low mass protostellar envelope. Basically, there's a sun-like star forming in the middle of it. Those are inferred magnetic field lines from dust polarization. That's the kind of stuff that I did. It was fun, but what I'm doing now is also fun. So that's my astronomy journey. And now where am I? I'm at the AES Corporation. Our motto is accelerating the future of energy together. We have, we're as they like to say here on the website, we're a next generation energy company, but it's much more than that. I mean, AES is an umbrella company on top of several dozen subsidiary companies, one of which used to be IPL, Indianapolis Power and Light, which is the local utility. That's why I happen to live here. I'm not really sure why the data team is focused here, but that's where many of us are, and the rest of us are spread all over the world. Our values are safety first, high standards, and all together. And right now we are basically using our expertise over 40 plus years of being in the energy industry post deregulation in the 80s to now move the world from what you might call dirty energy, like coal plants, for example, over to renewable resources. And we work a lot with all these things. So we work on solar and wind. I'm in particular going to be telling you about wind because that's the data I was working mostly with this year. We were one of the pioneers in energy storage. In the upper right, you see what are basically shipping containers full of batteries, which are very useful when you're using renewable resources like wind and solar that are not so predictable, not as predictable as a power plant that runs on gas or coal. We have utilities, including the one here in Indianapolis, and we have one in Dayton, Ohio, and one down in El Salvador, who I've also worked with. We run natural gas operations in the Caribbean. We have hydro plants in South America, Central America. So there's a lot of stuff going on at AES. And since the data science team at AES is basically an internal consulting group, we work on tons of different problems in all of these areas and more. So that's a general intro to AES, kind of an intro to this particular story that I'm telling you this year. I told you a story last year, I'll tell you another story next year, but this year's story starts with the fact that in particular over the last year or two, the number of solar and wind plants that have been dumping data into AES's servers is growing rapidly. And ideally, business with a capital B, meaning the people who I work for, you know, the people making the business decisions and looking at the KPIs, they need insights from dashboards, which I call BI, that's business intelligence, as well as AI/ML models. So ideally, when you plug in a new plant, you press go, it comes online, the data should be quote unquote BI and ML ready. You should be able to just make a dashboard. And in an ideal world, that would be possible, but alas, much of the time it is not. So here's the problem statement. For those of you who've done Six Sigma, you'll recognize this kind of thing. For those of you who haven't, if you transition into data science, I hope you have the opportunity to do a process improvement project. I really enjoy this kind of thing. So we're working on one right now that's around the project that we did this year. And the head of the fish, the Ishikawa fish diagram, where you're picking apart the problem that you have that's causing you all your pain points. The problem is that at AES, the operations teams, say a wind team, you know, trying to figure out what their wind farm is doing, are unable to gather and share insights about their assets, meaning say turbines, from data and analytics products. And while the data exists, the data are not governed in a way that enables consolidation or scaling for future growth. Okay, now, a couple of fun quotes from my manager. Businesses live or die with data. This was him telling me why I was on this project for the entire year when maybe I could have been doing something that looked more like standard data science. Also, data are meant to be useful, not pretty rocks sitting on a shelf. And this is kind of getting to the point, like the data are an asset, the last one. You've probably seen this in the blogosphere. Data exists at any company. Every company is a data company. We're all technology companies. But the thing is, what makes or breaks a company is what the company does with its data. And so you really need to be able to use the data, access the data, monetize the data, like make value out of the data. And that's where this year's work on harmonizing disparate data sources came in. So a key root cause of this problem statement that I showed you a couple of slides ago is the lack of data harmonization. And I'm going to show you pictorially what that means. So in this little plot down here, what I'm showing you are 5 so-called point IDs, which is a unique identifier in our data system called EDIPRO. You don't need to know what that is. Just know that it's a software that provides raw data. And the measurement, which is like what you as a human being would call it, is in the right-hand column. And this site looks pretty good. So for turbine 01, X temp underscore WTG01 is the ambient temperature for turbine 1. So that kind of makes sense. And if all of the sites look like this, we'd be pretty good. It would be essentially ML ready. Unfortunately, if you look at 6 of our sites, and there are many more than 6, this is the ambient temperature measurement for the one select turbine at 6 different wind farms. And you can see LOS, Los Olmos, on the 5th row. I showed you that before. And then just below it, for example, is Tucano in Brazil, TUC. For turbine 101, that 101 doesn't even exist in the point ID. Like this is the unique name for that data stream, and it's almost unreadable. And if you go to some of our other plants, in particular, like the gas plants, for example, some of the point IDs are actually not human readable. And so what you need to do, since the data were not governed when these plants were commissioned back at the beginning, and people named them whatever they wanted, we now have to create another data layer, a harmonization layer, to abstract out, to basically remove from our mind, from our vision, these point IDs in this column, and we have to invent new names that harmonize all of these data streams so that we can easily use them in models and dashboards. So now to the medallion architecture that I promised I would show you. This is kind of an okay analogy. It's not bronze, silver, gold in the like 3-2-1 Olympic idea. The idea is more like refining, which is also kind of a bad analogy because you don't refine bronze into gold unless you're an alchemist from the 1400s. But the idea is that bronze, just kind of, roll with it. Bronze is raw. Gold is very use case specific. So going back to bronze, the EDIPRO data I showed you before, SCADA data, if you've heard of that, it's basically just data coming off of a machine like a wind turbine. Trimark is a vendor that sells wind and solar data, and we use them, and they have a really nice way of organizing their data. So that's bronze. That's what like data engineering brings in the pipeline. And then gold is super specific for one particular use case. Say you have a problematic turbine, you want to make KPIs on what that one turbine is doing every hour. And so you filter out all the other turbines, you average the data down to an hour, and you have this little data set that you can then stick a dashboard on top of. That's gold. And in the liminal space in between is where we harmonize. It's this, and this is the space I've been working in for the whole year. You basically massage the bronze data enough and you get rid of those human unreadable identifiers, but you don't massage it too much that it's not generalizable. And so this is a really kind of tricky line to toe, but that's what we've been working on. It's been pretty good. It took a lot of work, but we've had some really good success now with this data platform, as we call it. So here's the architecture. This is actually stolen directly from Trimark. So Trimark did a really, really nice job. Focus on the tables on the left. So everything inside this dotted box is our silver layer. And these are basically, on the left, all metadata. You know, relatively small tables. Those sites here in the upper left. That's the latitude, the longitude, the time zone of the particular site. The devices here is the list of the turbines, you know, with maybe the make and the model, which is a really important bit of metadata to have for a wind site. And then these are really the key. So the way that they split up device types and point types. So a device type is the type of technology, like a tower or a nose cone or a blade. And the point types are the actual physical measurements, like a force in newtons or a speed in meters per second. And then down here in the points table is where the business basically has to do the legwork of harmonizing those data. So they go through all the turbines, they get the EDIPRO tag, which is that unreadable thing, and then they harmonize it with a name that we govern. So this is where data governance comes in. We have naming schemes, naming conventions, rules, and that's where you have that harmonization between the kind of undesired data stream tag and the new one that you're building in. And then we combine all these metadata tables into what's called the intervals table. That's kind of a term of art. Intervals is basically just the value at each timestamp for all these data streams. And then from that, you can stick a dashboard right on top of it, or you can build a gold layer that's another layer on top of it, as I said, where you filter and average, whatever you want. And so that's kind of the architecture in Miro form. And I just want to put this up. This is maybe kind of like a teaser for a talk next year, more on data governance and the data mesh. What we're really trying to do with this is get it out of the hands of digital. So I work on the digital team. We are not supposed to be experts in any data. You know, we business is experts in their domain. There are many, many business domains, finance, operations, etc. They're the ones who should be owning their data. And what we've actually done as a side part of this harmonization effort is built them a tool through this SharePoint interface, which is kind of, you know, it could be better, but it's pretty good. And they can fill out Excel documents or spreadsheets with the metadata that they want to add to this platform and submit it to the SharePoint. And through various Power Automate and Prefect other mechanisms, they can put the data in themselves. And that, I think, is the way that we're going to move forward here, at least at AES, with this idea of having business own their own data and be able to actually manage it themselves, which I think will lead to better quality. So here's what comes out of it. This is an example data for a dashboard that we have not built, but I just did a simple query here in BigQuery, which is our database of choice. And you can see I grayed out these point IDs here that you no longer need to know. And you can see we have here the unified ID. And then again, the point type ID, which is a temperature measurement, and the device type ID, which is just general, it's a turbine. And you have the site, and the value, and the timestamp. And this is how you can now have BI and ML ready data, where you can filter, you can sort, you know, very, very easily, either on the unified ID, which is basically the new name for that data stream, or any of the component parts of that unified ID. And so this kind of ex post facto seems really basic, but it actually required a lot of legwork, and it makes the end parts of building new dashboards and models so much easier. And so my last slide, I showed this last year, I tweaked it a tiny bit, but it's basically the same. Any questions on this later are most welcome. The transition is hard. Maybe not for everybody, but I think for a lot of people, it was particularly hard for me. I was in another country. Luckily, I could do it remotely. I was living down in Chile. I had 2 kids, you know, but when you need to do it, you need to do it. And there are a lot of us out there, like at this conference, you know, more every year, who've done it and can help you. You know, read Taka's slides first. Like that's really the place to start. I would say for me in particular, I had to convince myself to adopt a growth mindset. Drinking from a fire hose is It's what happens. I'm still drinking from a fire hose, and I've been working here for 2.5 years. You learn a lot, but it's actually a lot of fun. Some people dig drink from a fire hose. I really didn't, but now I'm cool with it. Get ready for tools. In astronomy, a lot of the times you just use Python and some other kind of homegrown software that may or may not be very good. In industry, you have budgets. Tools are expensive, but they can get paid for. And some of them are really fun. Now, of course, you get overwhelmed by them if you sign up for too many. Some of them get acquired, they disappear, they don't really work for you, whatever. But it's kind of a fun space to be in. I've done a lot of testing. I've had Google call me up and ask for my feedback on certain things that I thought were subpar. So it's good. It's fun. Now, this was a bone of contention last year, but I left it in anyway. Take a boot camp if you can. And I put the parenthetical this year of depending on boot camp quality. Do your homework. There are a lot of shysters out there, but I would not have gotten the job that I got as quickly as I got it without the boot camp that I did, which unfortunately doesn't exist anymore. It was called the Data Incubator, or TDI. But I assume there's some good ones out there. I do not know which ones they are right now, but just a piece of advice from somebody who did go through boot camp and found it very useful. And in the end, no Python, learn SQL. It's not that hard. I think it's really fun, honestly. And I would recommend knowing Git. You don't really have to on day one, but it's better if you go in, knowing what a merge request is, that kind of level. And so with that, I will wrap up and take any questions. Thank you very much.
Thank you very much, Chet. Any questions in the live audience here for Chet? Got one. Stand by.
In one of your slides, you mentioned not reinventing the wheel, and not just data related, but also could mean, in terms of modeling and stuff like that. Where do you think things are going now? For some of us, we did this transition some time ago, and we had the fun to build models and stuff doing that. But you think now that it's more about service delivery, scaling up, and all. Where do you think is this data science going in terms of career-wise, so we can let the others, the newcomers, know?
That's a good question. I mean, everybody who's giving a talk here is going to have a totally different perspective. I think maybe you might have had a different interpretation of what I put on the slide in terms of reinventing the wheel. What we're doing here is serving up the data in a way that makes it really easy it just makes it faster to build a model. So the model part, like what I hope I'm going to be doing with these data this year, can be just as fun and tricky and intellectual, as it was before. It's just this part is removing a lot of the legwork of having to call up the performance engineer and say, hey, I'm back. I need to build another model. Can you tell me again what the point IDs are for ambient temperature and wind speed? Because I need to make this other model. That's what I meant by reinventing the wheel. So the whole point of this was to basically maximize the time doing the fun stuff, like for an analyst to build a dashboard or a data scientist to build a model, and minimize the manual error-prone parts of doing the harmonization model by model. So I think that the fun data science, there's still tons of it out there. And I wouldn't worry that this is like signaling a change away from data science being fun or anything.
Just a reminder to folks in the chat who are watching on Zoom, you can ask a chat. There's the Q&A button should work, and I think Eva just posted in the chat about how to ask a question if you're on Zoom. Any other questions here? Eva, do we have any questions online?
No questions online.
Any more questions for chat here in the room? I just want to say shout out from another TDI alum. I did Data Incubator myself, chat, and back in the in-person days in 2018.
Yeah, cool.
All right, I think that was it. Thank you very much. Another round of applause. Our next speaker should be Andrew Schechtman-Rook from Capital One. Oh, he's here in person. Are you online? You're right there.
No, I'm not online today. Here, McLean. Yeah, Richmond, McLean, Plano, New York, Chicago. All right. There you go. All right, sweet. Can I get it on this machine too? Yeah, right. I just have to constantly look over awkwardly. All right, cool. Cool beans. No worries. It's not your fault. I'm not blaming you. It's fine. Okay. Hey folks, thanks for having me. Thanks for coming out. My name's Andrew. I learned something a few years ago in like my career that felt like it came like 10 years too late and has really influenced how I think about the work I do as a data scientist and the work that I did back when I was an astronomer. And so I thought I'd come here and try to share that all with you and see if maybe anybody else, would benefit from something I really wish I had known a long time ago. Also, just fair warning, there is at least one audience participation part of this talk, so just stay on your toes. All right, now let's move it. Sweet. Okay, so before I get into what I'm going to be talking about, just the obligatory, my background, where I came from, was mentioned. I'm at Capital One, right?
Yeah. Can you stand closer to the mic, please?
Closer to the mic.
Yeah.
Okay.
Or stand or speak louder.
I can probably do both.
Perfect.
Okay. So yeah, who am I? My background. So I got an undergraduate degree in astronomy from Case Western Reserve University in Cleveland. Then I did a PhD in astronomy at the University of Wisconsin in Madison. Then I was part of the inaugural cohort of the Data Incubator, one of those PhD to data science boot camps, which I just learned doesn't exist anymore. Oops. Well, that's what Chad said. Yeah, so I also am happy to talk about boot camps if people are interested. And then from there, I got connected to Capital One, specifically Capital One Labs, and that is where I've been for the last 10 years. So I won't go any deeper into any of that stuff, although I have lots of feelings and opinions on that if anybody's curious later. As to the topic at hand, the talk is called Pythonic Design Patterns for Data Science. What does any of that even mean? Right, what's a design pattern? If you're anything like me, when you first heard the term design pattern, you thought maybe like an arts and crafts project, right? That's not what we're talking about here, although I do really like that tile thing on the right. I think that's pretty cool. I wish I had come up with that myself, but no, we're talking about software design patterns, which I guess is not also that much more helpful, right? So, okay, something to do with software. What do I mean? So I think about it like this. When you're writing code, when you're designing software for a data analysis pipeline or for a tool that you're building or for some machine learning project or whatever, you have the very detailed line-by-line tactical decisions you're making around, hey, what do I need to write on this line to do the next thing I need to do? What's that line got to look like? What should my variable name be? How long should this line be? Do I want to call a function? What's that function going to be, et cetera? That's like a really detailed tactical perspective. Then on the other side, you have a very high-level architecture perspective around, okay, well, I have to solve this word problem with code. How do I structure that? This word problem might be like a year-long analytics project, right? It might be something very large and require a lot of moving pieces and possibly collaboration. That's a very high-level discussion, right? Instead of decorating a room, you're now thinking about planning out a city. Design patterns sit somewhere in the middle of that. They're the kind of decisions you make at a function by function level. If you're going to write a function or design a class or something, maybe at a couple of functions, that's when you're thinking about design patterns. So I'm going to show examples of design patterns. Don't worry, like I know that's not enough, but I want to motivate that part first by talking about why I think they're useful. I think they're useful for a couple of reasons. The biggest one is that you're using a pattern that maybe you're tweaking it a little bit, but it's mostly something that is off the shelf. It's been tried and tested, done before. Other people have said, yes, this is a good way to solve this class of problem, right? Or a good way to implement this kind of thing. These are techniques that are known. You're not writing something bespoke based on what you think you might need in the moment. And they're more likely to be durable, more flexible, anticipate problems that you don't even realize you're going to have yet, because other people have been through this and they've come out and said, these are good things and these help me, right? It also can help make your code more readable. If you're doing something that's a pattern that people know about and somebody else needs to look at your code, they can come and say, oh, okay, like here's a thing. It's not just bespoke. It's something I can recognize. I see what they're doing here, aha. And then they can help predict what is going to be next in your code, which, let's face it, is basically like most of the comprehending, right? If you can predict what's going to happen next and you say, ah, yes, I'm right, then that helps, a lot. So that's why I think they're very important. Now, there are a ton of design patterns because I'm not the only person who thinks they're important. This is a pretty deep field, maybe not quite a field, but a hobby that a lot of computer scientists have. This is from the Wikipedia page on design patterns. This is not the whole page. Don't read this. I'm not trying to tell you to read this, please don't. But there's a ton out here. They're not all relevant for anything you do. There are patterns that are better or worse in some languages than others, because programming languages work a little differently. There are some that are going to be completely inappropriate for a data analysis or an astronomy or data science pipeline because they're designed for people who are doing like web development or like API development, and they're about handling asynchronous connections or something like that more effectively. And so the question then becomes, okay, like what do you do from this giant list that most of them are probably not going to be relevant for what you want to do? And so here's where I come in. For the rest of the talk, I'm basically just going to be showing a few of the design patterns that I have felt are the most useful in my career. Now, originally this talk had 7 of those examples, and that was over an hour of content, so I cut it down to 3. This is not an inclusive list, but hopefully is enough to get your juices flowing and thinking about this stuff. And these are some of the ones that I found to be both the most useful, but also the ones that I didn't necessarily think about until I had been doing this for a really long time. All right, so we'll get right into the first one. All right, I know it's a faux pas to show code, right? It's up there with giant walls of text or, God forbid, math. I'm not gonna do math, thank goodness. But I think it's important to be able to show some kind of example, something concrete. And so this is just as simple as I could get it. This is a function that takes in a data frame and goes and iterates over every single column in that data frame, and then calculates the mean value of that column, and then inserts that mean value into any null rows of that column, right? So this is called imputation, mean imputation. This is something that I don't think I ever did in astronomy, but is very common in data science and machine learning, right? Hopefully it is tractable because I will be returning to this a few times, but this function, I will tell you, it works. It does impute the mean for every column that you pass it in a data frame, but it's also doing it in a way that I would say is somewhat shady. So here's the audience participation part. Does anybody have a guess on what I would argue is shady in this function here? Yep. Okay, so there's 2 shady things that are happening. The answer was the response was you're not doing type checking, so maybe you're taking the mean of a string, which would be bad, yes, but that is actually not what I was thinking of here. Yep.
We're taking mean, but you're also taking mean, which could have NANs already. So
Yeah.
then you get the NAN as the answer.
That's fair. The mean might not be NaN sensitive. NumPy, that is true, and you will get in trouble. Pandas is smart enough, and Pandas' mean is null ignorant on purpose. I think you might be able to tell it to not do that, but that is also not okay. So 2.5-ish shady things. Any more guesses? Mm-hmm.
The mean actually represents I guess the mean is a good way to measure what the average of the distribution is.
Yeah, the mean is good to measure the average of the distribution, sure.
No, I meant is that
Oh.
I guess.
Are there outliers and stuff? Is that what you're getting at? Yeah, okay, that's also problematic. We'll talk about that in a hot second. Yep.
Well, the first thing I'm looking at is that there's a for loop there.
Okay, yeah, should there be a for loop? Should we use broadcasting more effectively? This is actually probably okay in the sense that I don't think if you want to broadcast this over multiple dimensions, I think that the readability trade-offs, unless your data set is really wide, that's a really interesting. Anyway, maybe we can talk later. Yeah, you?
But that you're reassigning back to the same column?
Yeah, you're reassigning back to the same column. You are overwriting the data in place. You're not, in fact, this is essentially equivalent. You don't have to return data at all. You're mutating is kind of the more technical but also more fun term. Right, you're mutating the data, and you're not really being upfront about it, right? You're saying, hey, there's a thing, this function, it claims it returns the output. You think in your head, okay, data, it comes in, but no, actually, you're changing your input under the hood. And this is bad for a couple of reasons. I mean, the real problem is that this causes bugs that are incredibly hard to fix. I think that in my experience at least, it is a Python rite of passage for anybody learning to program Python that they will make a mistake where they spend like 6 hours debugging something that turns out to be because they accidentally changed their data when they didn't think they were doing that. It's like really bad, right? It's almost impossible to tell what's going on and when this happens, and like when you're trying to figure out what the hell, like it's so bad. So the name for that kind of function is an impure function, right? And I think about it like this, where you have like your function is this nice stream, and your impurity, or these nasty side effects, are like a giant polluting factory that are messing up your nice pure inputs and outputs. And so like that's nice for me because I don't want that. I don't want pollution in my river. And so instead you can get like a nice pure function that doesn't have any of that, and that's what you really want, right? And so generally speaking, in my opinion, that's better, it's cleaner, it's easier to read, you're less likely to accidentally shoot yourself in the foot that way. So how do you fix that function? The original function, it's basically the same thing. You just make an explicit copy, right? Sometimes it's good to make copies even if you're not sure what's gonna happen, because then you can be like, all right, this is now bulletproof. Python has copy implemented itself, but Python also has a standard module called copy that has a deep copy, which will recursively copy things for you and almost never fails to properly copy. That being said, I think in general this is better. There are exceptions, these are guidelines, not rules, right? There's not like, do this every single time, there's always exceptions. The exception for this one is if you have memory management challenges, right? If your data set is huge, a copy may not be the right thing to do because you may run out of memory. Pandas is not particularly friendly with memory, it will happily grab more than it needs. And so in that situation, it becomes more meaningful to do things in place because you don't have to carry around extra objects. This is actually carrying around 2 copies of the data frame at once, right? That being said, if you're gonna do that, try to be more explicit about it. Be like, hey, like this thing, certainly don't return data if you don't need to return the data, right? Return none, that helps make it more explicit. Have a doc string, talk about it more, be explicit, and make sure that people reading will understand what's going on. All right. Pattern 2. Now, this is the exact same function as before, right? I haven't changed anything, nothing up my sleeve. Right now, let's say you don't want to impute by the mean anymore because, like, I'll tell you the secret, like the mean is almost never what you want to use, that was your point. The mean is exposed to outliers and other things. You generally want to use the median, right? There are almost no circumstances where you want to use the mean. I'll state that it, like, very confidently, perhaps slightly more confidently than I should, but I've yet to see it in 10 years of my career. But if you have this code already, you probably don't want to like just rip out the mean and slap in the median. You might have backwards compatibility that you care about, or you don't want to like change things, or you want to provide more options for people. Maybe you're building this as a tool where some crazy person might want to use the mean and you don't want to like stop them from like doing something that you don't agree with, right? It's their choice. So what do you do in that case? It's really tempting to do this, right? I will tell you, this will work, right? You throw in a keyword argument, you default it to the string mean, and then you do like an if-else statement in the middle of your code that says, hey, let's just check and see what's going on, and then we'll use the appropriate function in pandas to do this, right? I'm gonna argue that this is not very pretty from an aesthetic sensibility and also from a maintainability perspective. You have repetition, first of all, you have these multiple clauses, which is only gonna get worse if you wanna add more capabilities. And you also have to think about error handling in a way that you didn't before, right? Like what happens if somebody capitalizes the M in mean or median? This will fail, this won't. In fact, it'll fail pretty awfully because like you don't have an else statement that's capturing stuff. So you're gonna need like some error handling, and it can get kind of gross pretty fast, right? And it's not a great user experience either. If you think about it, if you take a string keyword argument for mean, the user should expect to be able to pass in mean with any combination of upper and lowercase letters, but they might also want to pass average, right? That's the same thing. So this is not ideal. And then the question becomes, okay, but like this works though. It's very easy, I know this, right? What do I do instead? And so this is the second pattern. The neat thing about Python especially is that you're not restricted to passing in like strings and ints and floats into your functions. You can pass in like anything, including other functions. In fact, the image I got has them as like pink elephants because I think it's funnier, but they're treated internally the same as all the other boxes that are going in. And so you can do some really wild stuff with this knowledge. And the thing to solve this problem is called dependency injection, And so you may have heard of some of these things already, you may be already using some of these things, possibly not knowing the names. I certainly didn't know the names for a very long time. If you're already doing some of this stuff, great. Dependency injection is nice because it's one of those like computer sciencey terms, and you can look it up and you can Google it. And if you don't use Python, you can Google it and see if it applies to your language as well. And also, I really like it. It's another fun term, dependency injection. And so, what does that look like? What does it really mean? It means that you can just pass the function into your function, right? So you still have this additional keyword argument. You still change that piece of it. But now, instead of saying like the default is string mean, the default is actually a function, and the user can override that with whatever function they want, as long as that function just takes in one argument and then spits out a single value. And that gives you a tremendous amount of flexibility. Let's say maybe the user has some other crazy functions they want to pass in to this beyond just the mean or the median. You have that flexibility immediately. You've gotten that for free by using this pattern rather than by using the strings, which is not something that's going to extend very easily. And so that can be really, really powerful. All right, and then finally, the third pattern, we'll keep with this example even further. Now, this is, again, as before, this has the dependency injection and everything. Now, let's say you don't want to impute with the mean or the median, you want to impute with like some random percentile. That's a little far-fetched, like nobody's actually doing that as far as I'm aware. I can't recommend it, but for the purposes of this example, let's say you want to use the NumPy nan percentile function and impute like the 90th percentile or something, right? Just for the sake of argument. Now, I just talked about how great it was with dependency injection. You get all this flexibility for free, and then you pass this in and you're going to get an error, right? And you get an error because nan percentile actually takes 2 arguments. And as I said, the dependence, like the expected signature of the function we pass in is a single argument. So like, oops, that's not good. All right, so like all the things I just said are kind of invalidated by this example. And, you know, obviously not, or I wouldn't be talking about it. But that's the setup here, right? So how do you deal with this? And so this is another one of those like cool things you can do with functions. They're almost like infinitely malleable, especially in Python. And the technical term for what I'm about to explain is a closure. That's the other term you can Google if you want. Sometimes there's a subset of this called partial application, which relates to like somewhat more constrained use of the closure. They're really cool. You can do a lot with them. Basically, the previous dependency injection is using a function in an argument for another function. This is almost the reverse. You're defining functions inside of functions and then returning those functions, which is a little more complicated, I will grant you. It's not, I don't think, so bad, certainly not as bad as something like recursion is, but it has some of those vibes because of the nesting of the function definitions. That's what this looks like for this example. You're not changing the imputation code at all. You're just creating, a wrapper around the nan percentile function that pre-fills the argument, that is the percentile that you want. So you're basically creating a little shim, a compatibility shim, that then lets you pass in the function into your code the way the code expects it. And so this is really useful, both in terms of like taking full advantage of the flexibility of this code I happen to write here, but in general, a lot of times you're gonna see, especially if you get into some more advanced like packages like Torch or other things like that, like some of the Python machine learning libraries that you don't control, like you can't modify. This we can modify, but you may not be able to modify the source code for TensorFlow or something. And this allows you to bridge the gap between whatever those packages expect in terms of the functions you're passing into them and functions you're using, and convert them into like what you need it to be, right? And that can be very powerful. With this, you can essentially convert any function you want into the format that the imputation function takes, and then you're off to the races. And that's just incredibly powerful. You can do a whole lot. This is also a way that you can sort of store state in a function for use later, which normally you can't in functions. It's a little shady, honestly, but it's really neat. Functions in Python are just totally wild. They're so cool. You can do so much weird stuff with them. But that's also really powerful. Again, we're getting more complicated, but we're enabling a ton more functionality essentially for free, right? You don't have to touch the original code to do it. All right, so as I said, I don't have enough time to go through like all of my list of design patterns that I happen to personally like. But just to kind of start summing up, if you take away one thing from the talk, I think it's that a mental association with design patterns, and that's neat. or design patterns, and that's cool, and rainbows and unicorns and stuff like that. It's one thing. If you take away two things, I think it's really valuable, not just for design patterns, but in general, to take a step back. And when you're writing code, maybe you're trying to like get to a deadline, you're trying to do analysis really quickly for your advisor, or your boss, or something like that. Take a second when you're writing it and designing it, and rather than just being like line to line to line to line, that's very, I just got to get this done. Take a second and just think about how you are going to structure some of the bits of your code, and just take a second, take a cycle, and think a little bit harder about that. See, like, are there things I can use here where I can reuse patterns, where I can use things that somebody else might be able to read, or might be more flexible if when my advisor inevitably suggests that I like do this in a slightly different way next week, right? And then finally, if nothing else at all, hopefully you learned a couple of cool terms to impress your friends in computer science. So, real quick, last slide. If you're interested in this, hopefully you're interested in this, here are some additional resources. The one at the bottom, the Python design patterns, that's, I think, the best one. I would strongly recommend going there first, even though I put it on the bottom, that's my bad. Really well written. Not every design pattern is going to be appropriate for what you want to do, but at least if you're anything like me, it will like dramatically expand your horizons and start making you think critically about a lot of things that maybe you hadn't really before. It's really good. Very great start for any of this. And then I'm always happy to talk. I'm around today. You can find me on the internet. I think my LinkedIn profile is on the website. There's my blue sky on the screen. Happy to talk about this stuff. Happy to talk about virtually any of this stuff, honestly. All right, thanks, folks.
Thank you for that great talk. I had a thought about it, and I lost it. So I will ask for questions from the audience.
So you're in a code review and someone's not following these design patterns. What do you do?
I mean, that's extremely context dependent, as that's the standard data science answer, right? It depends. But generally speaking, I didn't know about these things until I'd been in industry for like 7 years, plus 7 years of PhD, right? So these are concepts that I talked to my cousin-in-law who's a computer scientist, a PhD in computer science, like yesterday, and I casually mentioned that I was going to give a talk on design patterns. He just nodded like, yeah, okay, that makes sense. But if you're anything like me, which I think is most of us, like your education in software engineering is piecemeal and weird. And so a lot of people aren't going to have these fundamentals. And so I think you have to have a lot of grace, right, in general. But I think you can also use a teaching opportunity. Maybe you say like, hey, like I will approve this PR, but I'm going to like give you a link to some of this stuff, or we'll talk about this. We'll do some mentorship. Maybe you decide to hold a firmer line because you've already established these patterns in the code base. I don't know. It really depends on you and the other person, right? But those are two of the more, I think, common paths for that.
I'm going to ask a question, just because at work, I'm known for always writing classes. I put everything into a class. How do you feel about compartmentalizing your code and using inheritance a lot and kind of using those design patterns? That's something you like to do? Yeah, so there's also plenty of design patterns around classes. I focused on the functions because that just turned out to be a little simpler, and I think, honestly, like neater to me. Like there's also a bunch of classes you can do. And I think that if you're going to write an imputation like code at all, you should probably put it in a class, but for the purposes of this, it was a lot easier to do it as a function. I think that in general, you have to be a little bit more, classes can be very, very useful, especially if you're writing code for other people to use. It's oftentimes very desirable to be able to create an object and then give that to somebody else to then use. But you do have to be a little bit thoughtful because you can go way over your head with some very complicated metaprogramming things. If you start using inheritance too much or meta classes, you can go way overboard with them to the point where you 6 months from now even will not understand it, let alone anybody else. Like I've seen that in code bases, and it's a bad scene. Oh, this never happened to me. No, it's happened a lot, actually. Once you inherit it too many times, then you can't follow what your code is doing. Any questions in the audience here? Another one? Or any questions online? Do we have any online questions?
No.
I've got another one here in the audience.
Just a follow-up question about your last design pattern example. Is it a design pattern if we just add like start args and keyword args which are supposed to be passed to the imputation function.
Are you saying like the imputation function, if you add like, oh, I see. If you add additional like arbitrary keyword
Yeah,
arguments,
like for
that then
percentile,
you
for
pass
example.
into the thing?
Yeah.
Yeah, you could do that too. That's another way to do it. As I said, these are guidelines. These are just different ways to do it. I think that general using star args and star quargs it's not what I reach for first, but it might be good in your use case, especially if you don't need to do a lot of this stuff, right? Again, use your common sense, right? I'm just providing like some suggestions and knowledge. I'm not saying you got to do this.
One more, quick one.
Thank you for the nice talk. It's actually lots of fun to see code. So we should have more of that. A question actually more on the background and particularly your transition, right, between astronomy and data science. In the previous talk we had, it will be hard. It's kind of hard. So I wonder, how was that transition for you?
Yeah, I mean, honestly, looking back on it now, I'm like, I don't understand how I did that. It was difficult. Finding companies, hiring data scientists was hard. I will say, like, I'm happy to talk about that, honestly, for a long time, probably more than you want to listen to it. But I also recognize that was 10 years ago, and I think that things have changed a lot. When I did this, data science was this hot new thing that didn't have enough people in it yet. And then 3 years ago, even, like, companies were hiring like crazy for all kinds of engineering and data positions. And now, like, in the last year, things have changed dramatically. And so I'm not 100% sure that my advice is actually going to track any longer. I'm happy to talk about it maybe like separately, or you can reach out and contact me, but I don't actually know if it's good advice anymore.
All right, thank you very much.
Thanks, folks.
All right, so as some of the questions have gone into more of the career stuff and the transition specifically, there are some events at AAS throughout the week, mostly tomorrow afternoon, about career stuff. Plus, you can always reach out to the individuals to ask them more. But I will mention a little bit more about that later in the week, or in the talks. But now, I'm going to attempt to keep switching between tabs and slides. Get out of there.
Shall I go ahead and share my screen?
I was going to give you a quick introduction, but...
Oh, delightful.
See, look, if I click enough times, I'll get it right. Julia Silge has been a contributor to ATDS for many, many years. She's currently an engineering manager at Posit PVC, and she's going to be telling us about Positron, a new IDE for scientific computing. So I will get out of that and go ahead and take over. That looks good.
All right, is that okay in the room?
Yes.
Awesome. Awesome. Well, thank you so much for that introduction, and thank you so much for having me. I'm really excited to be here today talking to you about the project that I've been working on for about the past 2 years or so. So before I dig into that, I will give you a little bit of background on who I am, because I think, you know, it really impacts the way I think about the tools that I build today. So my name is Julia Silge. Here are some places you can find me on GitHub and YouTube and Mastodon and my website and that type of thing. So my undergraduate degree is in physics. And to give you an idea of timing, because I think just like our previous speaker said, that really does impact how I think about what data science is and how to transition and whatnot. So I finished my undergrad degree in the year 2000, and then I finished my PhD in astronomy in the year 2005. My own when I was in astronomy, what I worked on was kinematics and dynamics of nearby galaxies. This is our friend Centaurus A from a paper about the black hole at the center of the Centaurus A. But what I actually did during my time in astronomy was write code to analyze data. I was an observational astronomer. I was in an era that kind of predates Python's real rise and kind of takeover of astronomy. So when I think about what were the actual technologies that I used, I mostly programmed in C, and I used tools like I made all my plots in Super Mongo, and I used a lot of awk and things to write my and that those experiences really impact how I think about tools for people who are working with data. Since I'm talking about IDEs, I will say that at the time when I was doing that, I used Emacs to write all of my code, whether that code was an awk script or it was C that I was writing. I used pretty bare bones. I was not an Emacs maximizer, you know, like I was using fairly bare bone Emacs, and that made made me think a lot about what are the tools that we use to kind of try to do the work that we are doing. And you know, just like our previous speaker said, I didn't have a lot of formal training in software engineering, even though what I actually spent most of my time doing was writing code. I didn't have the kind of professional perspective on what it meant to write code, on like what are you know, had I heard the phrase design patterns, or was I aware of how to use version control? And honestly, no. Like kind of training that I came up and got coming up through physics and astronomy was, of course, more about the science. And I thought that as what my real thing I was doing was, and the code that I was writing was like a way to get done the science that I wanted to do. So I, you know, since I'm standing here giving this talk with you all, you know, it is obvious I transitioned out of astronomy. I did a postdoc, taught as a visiting professor for a little bit, but then maybe around 10 years ago, like several of other speakers, I transitioned out of astronomy into this, at the time, newish world of data science. I worked, my first job coming out of academia, and some of the other sort of random things I did for a little bit. My first job, where my title was data scientist, I actually worked at a small consulting firm whose clients were NGOs and state and local government departments. And I still think that's kind of an interesting way into data science, is through the kind of nonprofit and NGO world, maybe versus trying to go straight to something like the tech industry. So that was great for me. It really gave me a lot of hands-on experience, and be able, in a place that had a lot of data, but people were not using it, a lot of low-hanging fruit. I transitioned, worked as a data scientist in a couple different jobs, did eventually land kind of like squarely in the tech industry working as a data scientist. And during that time, I got exposed to the open source ecosystem for data science tooling, contributed to open source packages, to open source software, and then eventually kind of made a transition from being someone who spent 80% of my time doing data science and maybe 20% of my time building tools for data scientists, either internal packages or open source packages. I kind of transitioned. I got a new job. I transitioned to being someone who then spent like 80% of my time building tools and 20% of my time doing data science of various kinds, either for data that we had, or for teaching purposes or book writing purposes, kind of like keeping my hand in, as it were. And I draw, when I think about that career, from like astronomer to data scientist to tool builder, I think about that career arc in light of my own interest in like, how do people get things done? Like, how is it that people go about approaching the tasks that they need to do? So the company that I work for now is called Posit, and some of you maybe like, I've never heard of that company before. So my company is the company formerly known as RStudio. So if you have you know, friends in grad school who are maybe in the life sciences or stats departments, you may have heard about RStudio. The use of RStudio, the IDE, is not as common in the physical sciences, but that's the company that we are. Our company, we changed our name a few years back because really what we do is we build tools for data scientists and for people to do scientific computing, for people to do data science. So some of these tools that you may be familiar with include RStudio is one of the most broadly used IDEs in the world with millions of people who download and use it every month. Another tool you may have heard of is Quarto. I was really excited to see that the website for our very Splinter meeting here was made with Quarto. It's I was like, this looks like a Quarto site to me, and I go in and I'm looking in the you view developer tools, and I'm like, ah, yes, Quarto site. So Quarto is a tool for scientific authoring, data-centric publishing. So things like, do you need to make slides? Do you need to make a website? Do you need to write a paper? And does that paper have a computational aspect to it? Like you need to run Python code as part of your website, paper, slides, etc. Shiny, which is a framework for making interactive data-centric apps, either in Python or in R. Great Tables is a package for making publication-ready tables in Python. And what I'm going to talk to you about, which is Positron. So Positron is I'm excited to talk about. It's a new IDE, and so I'm going to walk through a little bit about it so that you can understand. So the whoops, let me click here. Okay, so I'm going to tell you 3 things about Positron so that you can understand a little bit about it and maybe know whether it might be a good fit for you, whether you stay in astronomy, move into data science, or do something else. So the first thing I want to tell you is that Positron is a next generation data science IDE. So IDE, those words stand for Integrated Development Environment. It's a piece of software that allows you as a user to yourself develop software. So there's a ton of IDEs out there in the world. I want to tell you a little bit about what's like new and or different and or special about Positron, so you can understand like why are we building it, why is it being built in the way that it is, why is it built on the components it's built, and whether it might be a good fit for you. So this is a screenshot of Positron, and the first thing I want to say is that Positron is an IDE specifically for data scientists. It is a tool. It's not a general purpose software and engineering IDE. When I think about my time back, as an astronomer in grad school, like using Emacs. Emacs is one of the most general purpose tools, right, that could be out there in terms of like code editing. If you have used something like VS Code, that will come out, well, we're going to talk a little more about VS Code in just a moment. VS Code is a general software engineering code editing piece of software. So my experience coming from astronomy through data scientists, a core belief that I have is that people who are writing code for scientific computing, for data analysis, for data science, they are different from someone who is writing general purpose code. They're not worse. They're not doing bad things. They are just different. So this example here, this is someone who's like writing, they're using Quarto, which I just talked about a little bit, to write a report here. They have the person who's doing this has different needs than a general purpose software engineer who's maybe making a website or is building a software app. And I love working at Posit because like everyone has this understanding that a data science user is different from a person who is writing code for more general software engineering purposes. And the people at my company are huge proponents of code first data science, like not pointy clicky UI based tools, right? Like there's huge problems with GUI based tools or pointy clicky tools over code first approaches for data science, but tools that are built for a typical software engineer who is writing code, they're often not a good fit for someone who is writing code to analyze data. So all across the org at Posit, pretty much everything we do or make or build is informed by how deeply we know and believe in this, that like we can make tools for you specifically as someone doing scientific computing. We can make you more productive by building tools that are specifically for you and for the task that you have. And I really see connections from my background to how much I know that, like I know and believe this. And I think people working, in astronomy or physics or data science, like we often have this rep of like, oh my gosh, the code they write is so bad, right? Like it's not like code that someone with professional software engineering training would write. I wanted to reframe that as it's because it's different for good reasons. It's different because people have different needs. The second thing I want to say about Positron is that it is a tool for exploring data and for writing data-centric code. So data practice tends to involve, there is some code that we write or things that we do that are pretty much the same. But there are three sort of categories that are qualitatively different from general purpose software engineering. So I think these kind of fall into buckets like exploratory data analysis, where you are writing code in such a way that what you find in the data is in a loop with the code that you're writing. So it's not like you're like, I am deciding to create a mobile app and here's what it is and I can say what I will make ahead of time. Because what we're doing depends on the data itself, we end up in these iterative loops. The work that we do for data science, for scientific computing, inside or outside of industry, is more exploratory and iterative in nature. We also have a big need for reproducible authoring. Problems around reproducibility arise in the sciences, in data science, in data analysis, because when we run code, it's not just about the software, the code that is written and the dependencies of the software. You can pin all that, and then the results that you get can be different because the data that comes in is different. And so being able to create reproducible documents, whether that's with Quarto or some other tool, like that's a real need that people doing data science have. And then the other thing is publishing data artifacts. A data artifact can be a report, a website, an app, a pickled model object, right? Like we have these artifacts that we need to be able to publish in ways. So Positron is a tool for writing code and exploring data that is built to work well for you no matter what language you use for data science. It is built with this idea of being a multilingual IDE. So as of today, Positron works for Python and for R, but it is designed in a way to support other data science languages as they become important and get relatively less or more important in the data science ecosystem. So a lot of environments that are built for data analysis are specifically built to use one language for scientific computing. So tools that you may have heard about or used in this category include RStudio, which is made by the company I work for and is still around, still important. MATLAB, Spider for Python. Like there's a lot of these kinds of tools that are built. They're not general purpose tools like, say, VS Code. They're built specifically for data analysis, but they are built with one language in mind, whether that's R. RStudio is built for using R. MATLAB is, of course, built for using MATLAB, and Spider is built for using Python. So there are real limits to these kinds of tools or IDEs, especially for the high proportion of people who use multiple languages and when they're doing scientific computing or data science. This can happen literally on the same project. You can use more than one language in the same project. It can happen over the span of a week on different projects. Almost certainly it's going to happen over the span of a career. I think, I bet you talk to almost any of us, right, who are have been in astronomy and left, and like, are we using the same tools we used when we were in grad school 5 years ago, 10 years ago? Like we shift what tools we use over time. And like many of you are already familiar with this. I often see combinations of people working with R and Rust, or Python and JavaScript, or basically any data science language plus SQL, right? Like we're not always using one language, and so our tools need to be able to have this multiple, be able to use for these multiple languages. So here in this screenshot, what you see is a tool, is an example where we see these front end features, like there is a there are these front-end user-facing features that are about the tasks you need to do when you're analyzing data and doing data-specific work. So by contrast with the IDEs that are just for one language, Positron has these front-end user-facing features and then back-end language packs that provide the engines for those features or tasks. So here you see these. There's like a console, an interactive, a fully featured interactive REPL, like console, like better than better than like a Python REPL. There's a variables pane where we see what variables are defined in our environment that we want to be using right then. There's a place where we're seeing the plots, like what are the plots? Am I able to copy? Am I able to interact with the plots in a way that I can as useful, in addition to the place where you're editing your code? And so in this example that I'm showing you, this is Python, but if I was instead using R, I would be able to do that instead. And if I was using Python and JavaScript, I would be able to, since it's built for to use multiple languages at the same time, I can do something with Python plus something with JavaScript within the same within the same IDE. So it's built both to support multiple languages and to support the specific work that we do in when we're doing data science. All right, the last thing I want to say is that Positron is both familiar and extensible. So it's familiar probably to a lot of you that are in this room because it's built on the open source components that make up VS Code. So Positron is one of these forks of VS Code that you may have been seeing really popping up over, the last 6 months to a year. And I think it's, one of the people working on these, I think it's really interesting because these open source components, what you might call what is called code OSS, it's MIT licensed. And what that lets people who are tool builders do is kind of do a lot of experiments about what do people want when it comes to an IDE. Some of the ones that are coming out are like really AI first. Our take on this is we're like built for data science practitioners, and building on this substrate of code OSS allows us to focus on the data science features. We don't have to. We kind of make a deal, right? As someone who is on a fork of this other project, that we take the general purpose software engineering or software code editing features, we take those, and we don't have to worry about the general features that all kinds of people who write code need, and instead we can focus on the things that we're really good at as a company, which is build things for data scientists, for people doing scientific computing. The other great thing about going this direction is that it opens up the wide world of VS Code compatible extensions for users who are maybe less comfortable with VS Code. They want the data science specific IDE, but they want to be able to have this really incredible extension ecosystem that they want to be able to use things for. So Positron also feels familiar to many people because it is inspired by our studio. So if you were to imagine a spectrum from VS Code to our studio, an imaginary spectrum, right now Positron sits kind of somewhere on that spectrum. So here you see our studio-like interface with a console, a source editor, fully featured help right in your IDE, so you don't have to leave to go elsewhere to get help. You can focus. You don't have to break your flow state going somewhere else, looking up help for the function that you're using. But it's being used with Python instead of with R. So if you are listening to this, you may be thinking, oh my gosh, should I switch right now? Like, should I go and try out Positron right now? So Positron is an early stage project. It is currently in a public beta, is what we're calling it. So it's probably not a great fit if you are someone who is really happy with your code editing right now. But I want to highlight a few things that might make it worth you trying out. If you are currently a VS Code user, but you have struggled to make it a good fit for your data science workflows, you're like trying to cobble together different extensions to kind of make it like a data science IDE, and it's like a little bit disappointing. You're like, this isn't quite what I want. Then Positron may be a good fit for you. If you are a Jupyter Lab user and you are kind of frustrated with the guardrails and that it's not really a fully featured IDE, you're ready to kind of skill up in the kind of tool that you use, then I think that might be great for you to give it a try using Positron. I think this is probably rare, but if any of you are our studio users and you want more ability to extend and customize, and you use other languages than R, then of course Positron will be a great fit. So I will point you to our website, positron.posit.co, for installers and documentation. You can find us on GitHub at posit-dead/positron, and I'll drop some of these links into the Zoom chat here. And with that, I will say thank you very much, and see if we have maybe, I don't know, a moment or two for questions.
Thank you, Julia. Julia, I'm responsible for the Quarto website. That was me.
Excellent, excellent.
And I want to say the coolest feature I find in Positron, which I've played with a little bit, is the ability to click on a Parquet file and actually see what is inside without having to load anything, which is very cool.
Yeah. That uses DuckDB in like the WASM version of DuckDB to be able to do that, and it is pretty sweet. It is pretty sweet.
If you store data in Parquet files, and you should instead of CSV files, it is very cool.
It actually works for CSV and other things too, like Excel, like the, I actually am not sure if Excel works yet, but like anything that you can read with DuckDB, which is a lot of things, you can just click on it and it'll just open.
Awesome. All right, any questions here in the audience for Julia? I think I saw this hand first.
I wish you could have presented this earlier. I've been in this code for some time now, and I did a transition from RStudio because I switched from R to Python many years ago. And I haven't even tried Positron. Now the big boost I've been having in terms of productivity the last couple of years has been the ChatGPTs, the AI assisted. Is really helping me to code even faster, and sometimes and learn from my own style. So how is Positron capturing that?
Yeah. So right now, like today, the answer to that is that we take the same approach that many of the other forks of VS Code do, which is that there's kind of a ecosystem of extensions out there that provide kind of like different user interfaces for interacting with these large language models, these large language coding assistants. So a personal favorite of mine is Codium, and I know that one tends to work really well. And the way these tend to work is that the extension kind of lets you pick a user interface, and then they tend to be flexible in terms of the backend, like whether you're running a local LLM, whether you're connecting up your OpenAI API key to be able to get the backend there. I'm not going to share any details, but I will say we have bigger aspirations than that. And so I would hope to be able to say something a little more by the time we come out of beta, because I do think I don't think it's saying too much to say that like we think the value of Positron is that it's data science aware, and like a VS Code extension only knows what comes in and out of the extension host ecosystem, whereas Positron is built such that it knows more about the data science tasks you are able to do, and so we can have richer information to prompt an LLM with to get you more information. So I would say today we have the same answer as the other VS Code forks, which is extensions plus like flexible backends, and look to hear more from us this year on that.
Hi, Julia. This is Claudia. It's great to hear from you. I haven't seen you in a long time.
A long time.
For everyone else's awareness, we went to grad school together. So, but I had a question about, so right now you said it's in public beta. What happens after it comes out of public beta? And how easy will it be for people to access Positron?
Yeah. So Positron is, much like RStudio. So the answer to that is basically similar to how RStudio has worked. So it's a free to use desktop app, source available. You can come and see the source code that we use to make it. The license is permissive, like you can use it for commercial purposes. You of course can use it for like research and academic environments. If you're looking to use Positron in a server environment, we have support for remote SSH sessions. If you've used VS Code, you may have used this where you have the app locally, and then you're connecting to a server that has, for example, a ton of resources and the Python that so the like app is local on your laptop, and then the Python and say data and whatnot is remote on a server. My company does also have a server product. It's called Posit Workbench. And so that is like you log into a browser, much like Jupyter Lab, and then you have access to different kinds of IDEs where that's the actual IDE is on a server. And so that's the piece, that last piece that I said, that is a paid product. It's interesting working at a company that does a lot of open source software. And I would love to, maybe eventually talk about that, about kind of like how do people build a business on open source software. But like that's the brief answer is desktop app, always free, permissive license, remote SSH support, free, permissive license, and it's the server piece that is a paid product. Great question.
Let's thank Julia one more time.